Hello everyone. During the last week, our maintenance team got a call from a consumer wherein the MCCB was burnt and he could not receive the electrical supply. When our maintenance team went on the site, they found that the MCCB was burnt and there was no major sign of any short circuit. So friends, here the problem was that the MCCB was not installed in a proper manner. The selection of the ratings of MCB were wrong and also the connections were loose. So today we are going to see what is MCCB and understand its working and the selection process of MCCB. So MCCB stands for molded case circuit breaker. Here, it's an automatic electrical device that is crucial for safeguarding circuits from dangerous overloads, short circuit, and sudden current surges. Then these MCCBs can handle currents up to 2500 amperes and voltages up to 1.1 kV. So they have more current handling capacity and voltage handling capacity than our traditional counterparts such as miniature circuit breakers and other circuit breakers. So MCCBs offer a significant advantage of adjustable trip settings, allowing for more precise protection which is tailored to specific electrical requirements. Then we will see the key functions of MCCB, that is safety and control. MCCBs are engineered to provide comprehensive protection and control within the electrical system. They act as a critical guardian against various electrical faults. So first we will see how it provides overload protection. It prevents damage by tripping when the current exceeds the preset limits over an extended period, protecting equipment from overheating. So here we can preset the limits of current. If the current exceeds this preset value, then the MCCB will trip. Then next function is short circuit protection. MCCBs instantly interrupt extremely high fault currents measured in thousands of amperes to avoid catastrophic failure and fire hazards. Then it also offers manual switching, which allows for safe on and off control of the circuit, essential for maintenance procedures or emergency shutdowns, ensuring worker safety. Then it has adjustable trip setting. MCCB offers customizable current and time settings, providing tailored protection that can be fine-tuned to the specific load characteristics. So we can set the time settings and current setting according to our specific load characteristics. Then we have here the simplified MCCB connection wiring diagram. There are input terminals which are connected to the main power supply on the bottom side of the MCCB. So here we have input main power supply. Then we have output terminals which connect directly to the electrical load, that is machinery or distribution panel on the top side. So we have control wiring, which is optional connection for remote trip and close coils, enabling automation or emergency control from a distance. Then we have auxiliary contacts, which are small contacts used for signaling, providing information about the breaker's status, that is on and off, or trip to control systems or indicators. So this is about the connection and physical layout of the MCCB. Then here is the construction of the components of MCCB. An MCCB is marvel of electrical engineering, with each component playing a vital role in its protective capabilities. First is molded case. It's a durable insulated housing that encases all internal parts, providing mechanical strength and preventing external interference. Then it has arc jet equipped with ferromagnetic plates. It rapidly extinguishes the intense electrical arc generated when contacts separate during the fault. Then it has magnetic trip unit. It's a solenoid coil that responds to short circuit currents, creating a magnetic field strong enough to trip the breaker almost instantly. Then its contacts comprising fixed and moving parts. These allow current to flow when closed and interrupt it when opened, essentially for circuit control. Then it also has a thermal trip unit. It's a bimetallic strip designed to detect overload currents by bending as it hits up, initiating the tripping mechanism. Then the operating mechanism includes mechanical linkage and a manual handle, ensuring trip-free design where the breaker can trip even if the handle is held on. The principle of operation, it has thermal trip for overload protection. The thermal trip mechanism is the MCCB's first line of defense against sustained overcurrents. The current flow, the normal operating current passes through a bimetallic strip within the MCCB, then heating and bending. When an overload occurs, the excess current hits the bimetallic strip. Because the two metals in the strip expand at different rates, it causes the strip to bend. It gives trip activation signal. If the overload persists, the bending of the trip reaches a critical point, physically triggering the trip mechanism to open the MCCB's contact. And it also has inverse time delay. This mechanism inherently provides an inverse time delay. The higher the overload current, the faster the metallic strip heats up and bends, resulting in a quicker trip. This prevents nuance tripping for momentary inrush currents while ensuring protection for sustained overload. Then the next principle of operation is magnetic trip for short circuit protection. So fault current surge. In an event of short circuit, an extremely high current flows instantly through the solenoid coil within the MCCB. Then it gives a strong magnetic field. This surge of current generates a powerful magnetic field around the coil. The strong magnetic force rapidly attracts an armature, which in turn pulls the trip latch. This immediately releases the main contacts, causing the breaker to open. Speed and precision. This magnetic tripping action is incredibly fast, typically occurring within milliseconds, approximately 0.04 seconds, making it vital for preventing extensive damage from severe short circuit. Then the coordination on large MCCBs. These magnetic trip settings can be adjusted, allowing for selective coordination with other protective devices in an electrical network, ensuring only the affected circuit trips. So this was about the principle of operation. It has two protection, that is thermal protection and short circuit protection. So we will see how MCCB protects our electrical system, a real world example. Consider an industrial setting where the MCCB is safeguarding a critical motor. The motor is jammed and overloaded. In this case, an industrial motor, perhaps driving a conveyor belt, experiences a mechanical jam. This causes it to draw excessive current far beyond its normal operating limits. Then the thermal trip activation. In this case, MCCB's thermal trip unit detects its sustained overcurrent. The bimetallic strip heats up and bends, initiating the trip mechanism. This helps in preventing the motor damage. When the MCCB trips, cutting power to the motor before it can overheat and suffer permanent damage to its windings or internal components. Then cable fault or short circuit. Later, a cable is connected to another part of the system is accidentally damaged, causing a sudden and severe short circuit. The magnetic trip and isolation activity comes in, wherein the MCCB's magnetic trip unit instantly detects the massive fault current and trips, isolating the faulty section within milliseconds, preventing fire or further system damage. And it also offers a safe restart. After the fault is cleared and the system is inspected, the MCCBs can be manually reset, allowing for safe restoration of power. So we have seen a real world example wherein the motor was jammed and overloaded. So what are the advantages of MCCBs over other protection devices? MCCBs offer distinct benefits that make them preferred choice for various electrical applications. First would be higher current ratings. As we have discussed, they are capable of handling significantly larger currents up to the value of 2500 amperes compared to MCBs, making them suitable for heavy industrial loads. And it has adjustable trip settings which provide flexibility to precisely tailor protection characteristics, optimizing coordination and preventing unnecessary shutdowns. Then they are reusable and resettable. Unlike single-use fuses, MCCBs can be reset after tripping, offering a more cost-effective and convenient solution for fault clearance. MCCBs have a robust design. The compact molded case construction ensures durability and reliability even in harsh environmental conditions. Then they have versatility of applications. That is, they are ideal for broad range of uses, from protecting main distribution boards in commercial buildings to individual machinery in industrial plants. Then what we can conclude here is that MCCBs are essential for electrical safety and reliability. Molded case circuit breakers are indispensable components in modern electrical infrastructure. They provide advanced protection. MCCBs seamlessly combine sophisticated protection mechanism with operational flexibility, adapting to diverse electrical demands. Then they have preventive measures. They are crucial for preventing devastating electrical fires, safeguarding valuable equipment from damage, and minimizing costly operation downtimes. Then they are powering the designs. A thorough understanding of MCCB's functions and their operational principles empowers engineers and technicians to design and maintain safer, more resilient and electrical systems. Then they have long-term investment. Investing in high-quality MCCBs ensures dependable long-term circuit protection, contributing to the overall integrity and safety of any electrical installations. So in this way, MCCBs offer a very robust electrical safety and control wherein we can protect our electrical equipment and electrical systems.